Here we're asked to check whether the series given converge absolutely, conditionally, or diverge. Now my gut feeling about this first series is that the absolute values should be bounded by something like 1 over n squared as n goes to infinity. So I'm going to check for absolute convergence. Now I know that the absolute value of cosine of anything is less than or equal to 1, so the absolute value of cosine n to the n over n squared minus n plus 1 is always less than or equal to 1 over n squared minus n plus 1. Now if I can show that the sum of 1 over n squared minus n plus 1 converges, then I know that the sum from 1 to infinity of the absolute values of cosine n to the n over n squared minus 1 also converge, and therefore my given series will be absolutely convergent. And now to show that the sum of 1 over n squared minus n plus 1 converges, I'm going to use the limit comparison test. And the obvious thing to compare it to is the p-series, the sum from 1 to infinity of 1 over n squared, which I know converges because it's a p-series with p equals 2, which is greater than 1. And so to apply the limit comparison test, I take the limit as n goes to infinity of 1 over n squared over 1 over n squared minus n plus 1. And then I invert that fraction in the denominator to get the limit as n goes to infinity of n squared minus n plus 1 over n squared. And then I divide through by the n squared, and I get that that limit equals 1, which is not equal to 0. Therefore, my conclusion is that both of these series do the same thing, and since I know that the sum of 1 over n squared converges, I now know that both of these series converge. Now, by the ordinary comparison test, I can conclude that the sum of the absolute value of cosine n to the n over n squared minus n plus 1 also converges, and therefore the original series, the sum of cosine n to the n over n squared minus n plus 1, converges absolutely. Now for the second series on the list, it looks to me like the limit of the terms of the series might not actually be equal to 0. That's because I can see that 2n squared over n squared plus 1 is going to go to 2 just from experience. So this looks like it might be a job for the divergence test. So checking the details, we have that the limit as n goes to infinity of minus 1 to the n times 2n squared over n squared plus 1 exists only if the limit as n goes to infinity of 2n squared over n squared plus 1 is 0. But when we calculate the limit as n goes to infinity of 2n squared over n squared plus 1, dividing above and below by n squared, we see that this is the limit as n goes to infinity of 2 over 1 plus 1 over n squared, which is 2. And this is certainly not equal to 0. So we can conclude that the limit as n goes to infinity of the terms of this series is not equal to 0. In fact, the limit doesn't even exist. Therefore, our series diverges by the divergence test. Now, this last series is an obvious candidate for the ratio test. Writing out the details, we have that the limit as n goes to infinity of the absolute value of an plus 1 over the absolute value of an is the limit as n goes to infinity of 3 to the n plus 1 over 2 times n plus 1 factorial over 3 to the n over 2 times n factorial. when we invert those fractions and cancel powers and factorials, we get that this is the limit as n goes to infinity of 3 over n plus 1, which is, of course, 0. Since our limit is less than 1, we can say that the series converges absolutely by the ratio test.